Hello and welcome to the next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we had discussed about various loss functions that can be used for training ML models, and having started with mean squared error as well as the mean absolute error, we moved on to other types of loss functions like the mean squared logarithmic error, the mean absolute percentage error as well as the logistic error. So in today's lecture we will take our discussion forward and look at a few more loss functions that will complete our discussion of this concept in machine learning. So let us go ahead and get started. So the loss function we are discussing today, that is the sixth loss function that we have discussed, and this is the softmax loss. And like I had mentioned before getting here, we have already discussed several other loss functions in ML, and that includes your mean squared error, mean absolute error, then the mean absolute percentage error, right, shortened as MAPE. The MSE is the mean squared error and MAE is short for the mean absolute error. We also looked at the mean squared logarithmic error, the MSLE, and we looked at the log loss, right, which is used for logistic regression. So the softmax loss is the sixth loss function we are discussing, and as you know from one of the lectures before, this is used in multi-class classification. So for multi-class classification problems, we employ the softmax loss. Okay. It is also called the categorical cross-entropy loss. Just like the binary cross-entropy loss, and it is defined as follows. So L softmax equals minus 1 over n, sum I going from 1 to n, so sum over all the data points, sum k going from 1 to capital K, so sum over all the classes, an indicator function capital I yi equals k, and then log of the probability of y equals k given the feature vector x, right. So this is how the softmax loss function looks, and I have already introduced this indicator function before. So I yi equals k is equal to 1 if yi is k and it's 0 otherwise. So if yi is not equal to k. Okay, so that is the indicator function, and n you already know is the number of data points, and capital K is the number of classes that are there in your ML model, and small I is the index for small I is the index for the data point and small k is the index for the class, right. So I hope this notation is clear to you. Now you can take this softmax loss and consider what happens when you have only two classes, right. So let us go ahead and try that out. So if you considered the softmax loss and only two classes, so let us do that. So considering only two classes, right, indexed by the numbers 0 and 1, the categorical cross entropy loss function can be written as, right, L softmax is minus 1 over n sum I going from 1 to n. Now inside there is a summation over the classes, and here in this case we have only two classes. So k goes from 1 to 2, right, and your I yi equal to k, right, is what you would typically write, but in this case of course we are saying that yi can take either 0 or 1 as the values. So if k goes from 1 to 2, you should write yi equals k minus 1, right, because only then yi can take the values 0 and 1. Then log of p y equals k minus 1 given x, right. So this is what our categorical cross entropy loss function looks like, right. Now you can expand this summation here, this summation can be expanded. Let us go ahead and do that. So this becomes minus 1 over n sum I going from 1 to n, right, and these two terms, the first term is the indicator function yi equals 0 because k is 1. So yi is 0 log of the probability of y being equal to 0 given xi plus the indicator function of yi equals k minus 1. Now k is 2, so k minus 1 is 1. So indicator of yi equals 1 times log of p y equals 1 given xi. Okay. So this is how the loss function looks, and we can simplify it even further, right. So if you want to write down I yi equal to 0, right, how does it look, right, how does it look? So I yi equals 0 is basically 1 if yi equals 0 and it's 0 if yi equals 1, right. So immediately you see that this indicator function is 1 if the variable is 0 and it's 0 if the variable is 1. So you can simply write it as 1 minus yi, right. So if yi equals 0 you will get 1, and if yi is 1 you will get 0, right. So I am going to replace this indicator function here with 1 minus yi. So this becomes 1 minus yi followed by log of the probability of y equals 0. So usually if you remember, right, in logistic regression we use the logistic function, and the logistic function defines the probability of y being equal to 1. So if we want the probability of y being equal to 0, that is just 1 minus the probability of it being equal to 1, right, and that probability is represented by this yi hat, right. So this is the probability of y being equal to 1 given x, right. So therefore we can replace this term here by 1 minus yi hat. I hope this is clear to you. Now we will go on to the next term. This next term here has the indicator function for yi equal to 1. So how can this be written? So yi equal to 1 is 1 if yi is 1 and it's 0 if yi equals 0. So here you see that the indicator is 1 if yi is 1 and it's 0 if yi is 0. So therefore the indicator is simply equal to yi itself, right. So this term we can replace by yi, and finally the log of py equals 1, that is simply the output of the logistic function, right. So that is log of yi hat. So essentially what we have done here is we have simplified the softmax loss function to be equal to this expression, right, when you have only two classes. So L softmax when you have only two classes reduces to minus 1 over n sum I going from 1 to n 1 minus yi log 1 minus yi hat plus yi log yi hat. Okay. This is exactly the same as the log loss function. So this is for two classes, right. So therefore we have shown that the softmax loss reduces to the binary cross entropy loss or the log loss for a binary classification problem. And this seeks to convey that our formalism is consistent, right. The formalism we have developed for softmax regression is reducing to the formalism we have for binary, right, classification problems through logistic regression. So I hope it makes sense to you. Okay. If that is clear, we can move on to the next loss function that we will be discussing, and this one is known as the Tweedie loss function. It is a somewhat less encountered loss function. However, its utility in the core engineering disciplines is actually quite important. So this Tweedie loss function is a family of loss functions which are used for data containing a mix of very low quantities and other continuous positive values, okay, which are skewed. So if your data is distributed normally or does not have a tail, then you do not really need to use the Tweedie loss function. However, right, if you have things like if you are into weather forecasting and you want to predict the rainfall, right. So rainfall can be very low, right, 0 on some days and other days it is a continuous positive number. Things like energy consumption which can fall or rise during the day, right, and even things like a nanopore probability in a 2D material, and this relates to the data set, right, that I had introduced in the tutorial that we had carried out in Python, wherein you had an Excel file containing data about probabilities and formation times of nanopores in graphene, which is a 2-dimensional material. Alright, so how does this Tweedie loss function look like? So, the Tweedie loss function is given as L Tweedie equals 1 over n some I going from 1 to n, and like I said, it is a family of loss functions, and there is a parameter which you can use to control this loss function. You have to specify that parameter. So, that parameter I will call by v. So, the Tweedie loss function is yi minus yi hat squared if that parameter v is equal to 0, okay. And this of course is just the mean squared error loss function, right. In other cases it is slightly different, right. For example, for v equals 1 you get what is called the Poisson deviance, and for v equals 2 you get what is called the gamma deviance. So, for v equals 1 you can write twice yi log of yi by yi hat plus yi hat minus yi, okay. So, this is for v equals 1. For v equals 2 you have twice of log of yi hat by yi plus yi divided by yi hat minus 1. And finally, it is a slightly more complex expression, twice of the maximum of yi comma 0 raised to the power 2 minus v divided by 1 minus v 2 minus v minus yi hat to the powered 1 minus v divided by 1 minus v plus yi hat divided by 2 minus v divided by 2 minus v. And this is if in these other cases, right, when v is not 0 or 1 or 2. Okay. So, it is a fairly complex family of distributions, and like I said and I want to reiterate, your v equals 0 corresponds to the mean squared error, v equals 1 corresponds to the Poisson deviance, and v equals 2 corresponds to the gamma deviance. Okay. So, in our case, for example, if you looked at our study on nanopore probabilities, prediction in a 2D material, we got best performance on the test set when the model was trained with a Tweedie loss function. With the v parameter equals 1.5, right. So, in some sense you can try to understand, right, what is the loss function that best describes your data set in terms of it being able to generalize more broadly to the unseen test data. And finally, I want to introduce a few more loss functions that are available in scikit-learn, and it is useful to know that these exist, but you may or may not end up using them in your ML model deployment. So, these are some other loss functions. and I will take a couple of examples. Like I said, these are available in scikit-learn, which is a Python package for ML. In one of the previous tutorials we had discussed about this package, and hopefully you will be using sklearn or scikit-learn in the future. So what are these two additional loss functions that I want to discuss? One of them is called the median absolute error. So it is an extension of the concept of the mean absolute error to the median. So it is abbreviated as MEDAE. Median absolute error is basically the median of the errors yi minus y1, y1 minus y1 hat, y2 minus y2 hat up to yn minus yn hat. So the median of these errors will tell you the loss function value. So that is one particular loss function, and the other one is called the max error, right. In this case you are mainly considered about the maximum error, right, that has been incurred. That is max over all the data points of yi minus yi hat. Okay. So like I said, it is useful to know about these loss functions. Perhaps you are working in a problem where you have to use some of these, but in most cases the other loss functions that I have discussed would be the ones that you will be deploying. So this brings me to the end of this particular lecture. In this lecture we continued our discussion of the loss functions that are deployed in machine learning models, and particularly we spoke about several new kinds of loss functions that we had not discussed before, and these include the Tweedie loss function, the Softmax loss function, as well as concepts like the median absolute error loss function and the max error loss function. And previously we had also discussed other concepts like the mean squared error, the mean absolute error, the mean squared logarithmic error, as well as the log loss function. And for some of these loss functions we had said that there is a statistical justification for using them. Particularly we had shown that the concept of the maximum likelihood estimation of the parameters, it leads to the particular loss function that we have considered. For example, for Gaussian distributed noise, the maximum likelihood estimation gives you the mean squared error. For a log normally distributed noise you get the mean squared logarithmic error. For a Bernoulli distribution you get the log loss or the logistic loss, and therefore some of these loss functions are rooted in kind of our statistical understanding, others are born out of convenience and practicality. For example, the mean absolute percentage error, if you want to ensure that the percentage error of your prediction is within a certain number, or even things like Tweedie loss, which is very useful in distributions with a tail, right. Let us say you have a lot of data with a very low value and then some other data with continuous positive values. So I hope this lecture completes our discussion of loss functions used in machine learning, and I hope that you will continue to learn more and to explore these as we proceed on our journey towards applying machine learning to core engineering problems. Thank you for joining us today, and I look forward to seeing you next time.